Homogeneous nucleation during solidification of metals. In the linked video, we have already explained in detail that the presence of nuclei is a necessary condition for the solidification of melts. In this video, we therefore take a closer look at the process of homogeneous nucleation. To understand the processes involved in the homogeneous nucleation of metals during solidification, the process must be considered from an energetic point of view. In this context, the so-called Gibbs energy plays a central role. The Gibbs energy is often also referred to as free energy or free enthalpy. As a state function, the Gibbs energy can be determined from the enthalpy of the substance, the entropy, and the temperature is shown. The Gibbs energy is the decisive measure of whether a chemical reaction or a thermodynamic process at constant temperature and pressure, which is usually the case in a solidification process, proceeds spontaneously with a release of energy, or must be forced by an input of energy. When the Gibbs energy increases in a reaction or process, it requires an input of energy from an external source. This is called an endergonic reaction. The energetically higher final state has the consequence that the reaction does not proceed spontaneously. If, on the other hand, the Gibbs energy decreases during a reaction, this process will proceed voluntarily with a release of energy, and thus the energetically more favorable state will result. This is called an exergonic process. If, on the other hand, the Gibbs energy of a process does not change, the reaction proceeds in the same way in one direction as in the other. This is referred to as stable thermodynamic equilibrium. The diagram shows the schematic course of the Gibbs energy as a function of temperature for the solid, liquid, and gaseous state of a substance. It can be seen that below a certain temperature, the Gibbs energy of the solid state is energetically more favorable than that of the liquid state. The intersection of the two Gibbs curves indicates the solidification point or, in the opposite case, the melting point of the substance. At the solidification point, the Gibbs energy of the liquid and solid states is obviously the same. Likewise, the vaporization or condensation temperature can be defined as the intersection of the Gibbs curves between the liquid and gaseous states. In principle, only the state of matter with the lowest Gibbs energy is in stable thermodynamic equilibrium. If the temperature falls below the solidification point, the liquid state is no longer stable due to the higher Gibbs energy. Rather, a decrease in Gibbs energy occurs during the transition from the liquid to the solid state. Therefore, below the solidification point, the Gibbs energy decreases as the state of the substance changes from liquid to solid. This phase transition thus strives to take place spontaneously, and the substance will change to the liquid state with the lower Gibbs energy, releasing energy in the process. The difference between the Gibbs energies of two states thus represents the drive for substances to change their state of matter when falling below or exceeding a certain temperature, thereby assuming the state with the lowest possible Gibbs energy. This fact already shows that simply reaching the solidification point is not sufficient to cause a liquid to solidify. A drive for solidification is only given if there is a difference in the Gibbs energy and thus a drop below the solidification temperature. Therefore, a so-called supercooling is necessary. The latent heat of transformation during the phase transition can also be determined from the diagram. For example, the difference in Gibbs energies between the solid and liquid states at absolute zero corresponds to the enthalpy of solidification of the substance. In the same way, the enthalpy of condensation can be determined in the difference in Gibbs energy between the liquid and gaseous states at absolute zero. The diagram can be represented in a much more general way if one considers the Gibbs energy per unit mass instead of the absolute energy amounts. One then speaks of the specific Gibbs energy. The latent heat energies then correspond to the specific heats of transformation, which describe the latent heats per kilogram of mass. The specific Gibbs energy is then defined by the specific enthalpy and the specific entropy. Although supercooling is now in principle a drive for phase transition and the process strives to run by itself, it does not take place spontaneously. This is because an important influencing variable, which also affects the Gibbs energy of a solidifying nucleus, has not yet been taken into account. If a nucleus is formed in a melt, it obviously has a solid surface. Energy is required to form such a surface due to the attractive forces on the nucleus surface. This is called surface energy, which is required for the formation of the solid surface during crystallization. Even if a nucleus is to grow, surface energy is always required so that the crystal can increase its surface area. The energy required to form a solid surface and thus trigger the phase transition in the first place is generally referred to as the activation energy. It should be noted that the Gibbs curves shown refer only to the energetic states in the liquid and solid states, which means only to the volume, so to speak. The energies required for surface formation during a phase transition, such as surface energy, are not taken into account. For a better differentiation, we therefore denote the Gibbs energy of a considered volume in the index with the letter V. The change in the Gibbs energy of a just solidified nucleus when the solidification temperature is undershot can thus be mathematically attributed to two essential terms, which are explained in more detail in the following. The term marked in blue results from the already explained lower Gibbs energy of the solid state compared to the liquid state. As long as the temperature is below the solidification point, this term is always negative. This is because the solid state below the solidification point has a lower Gibbs energy than the liquid state. This means that below the solidification temperature, the energy content of the solidified nucleus volume is lower than in the liquid state by the amount delta GV. Only under the assumption that a solid nucleus forms above the solidification temperature due to statistical fluctuations would this term be positive. This is because above the solidification point, the solid state has a higher Gibbs energy than the liquid phase. Such a situation will be discussed in more detail later. The considered term delta GV can be determined by the specific Gibbs energy and the corresponding mass of the momentarily solidified nucleus. We can determine the mass of the nucleus from the product of density and nucleus volume. For the sake of simplicity, a spherical nucleus is assumed in the following. In this case, the volume of the solid nucleus corresponds to a spherical volume with 4/3 pi times r to the power of 3. It can thus be seen at first that the change in Gibbs energy is proportional to the third power of the nucleus radius. Furthermore, it can be seen that the change in Gibbs energy is obviously influenced by the specific Gibbs energy delta GV. As is immediately evident from the diagram, this specific change in Gibbs energy depends in particular on the supercooling delta T of the nucleus. If one neglects the curvature of the Gibbs curves in the case of supercooling, the corresponding relationship can be derived by using the intercept theorem, also known as Thales's theorem. This states in this case that the ratio of the change of the specific Gibbs energy and the specific heat of solidification is equal to the ratio of the supercooling and the solidification temperature, provided that the temperature is given in the unit Kelvin. The change in the specific Gibbs energy when the solidification point is undershot is thus linked to the respective supercooling, as shown. We now use this expression in our original equation. Overall, this gives the given equation for calculating the change in Gibbs energy when a nucleus of radius r forms at supercooling delta T. Since it is common to state the supercooling delta T as a positive value, we introduce a negative sign at this point because, as explained earlier, the Gibbs energy of the solid state is lower than that of the liquid state when supercooled. Note that the Gibbs energy term just derived refers only to the energy content of the nucleus volume. One could therefore also speak of the volume energy. In the following, we will take a closer look at the second term, which describes the energy content of the nucleus surface, the surface energy. As already explained, the surface energy must also be taken into account when a nucleus is formed. The second term of the equation, already explained, serves this purpose. This term leads to an increase in the Gibbs energy, since energy has to be supplied to form the solid surface. This term is therefore always positive, regardless of whether the nucleus forms above or below the solidification point due to thermal fluctuations. The surface energy is the product of the surface tension gamma and the surface area of the spherical nucleus. Note that the surface tension is basically the surface energy per unit area. Multiplying the surface tension by the surface area of the nucleus therefore gives the total energy of the nucleus surface. The surface area of the spherical nucleus is determined by 4 pi r squared. Overall, the change in Gibbs energy of a spherical nucleus with radius r at a given supercooling delta T can be determined as shown. The interpretation of this equation is discussed in more detail in the following. For temperatures above the solidification point, the supercooling is mathematically negative and thus both terms are positive. While in this case the term marked in red for the surface energy increases with the square of the nucleus radius, the term marked in blue for the volume energy increases with the third power of the nucleus radius. For this case, the diagram shows the change in Gibbs energy for the nucleus as the sum of the two terms with increasing radius. In any case, the Gibbs energy of the nucleus will increase. Consequently, a stable thermodynamic equilibrium between the solidified nucleus and the rest of the melt will not be established. Although a solid nucleus may form, it will quickly dissolve by releasing energy due to the unstable state and will seek a minimum Gibbs energy. Thus, above the solidification point, the nuclei formed are unstable and dissolve. However, the diagram only becomes interesting when the temperature of the melt or nucleus is below the solidification point and thus supercooling is present. In this case, the first term of the equation becomes negative. For this case, the diagram shows the course of the change in the Gibbs energy of the nucleus as a function of the nucleus radius. The curve now shows a maximum. This curve will be interpreted in more detail in the following. First, we assume that a solid nucleus with radius r1, which lies to the left of the maximum of the Gibbs curve, is formed by chance. To form such a nucleus, the Gibbs energy must obviously be increased by a certain amount delta G. This is done by statistical fluctuations in the thermal energy of the melt, which can supply this amount of energy in the short term. If the nucleus is to grow further and thus initiate the solidification process, it must obviously become larger. According to the diagram, however, an increase of the radius is only possible with a further increase of the Gibbs energy. However, as already explained, such an increase in Gibbs energy does not spontaneously occur. Rather, the decrease of the Gibbs energy and thus the decrease of the size of the nucleus is more probable. The consequence is therefore that the formed nucleus dissolves again with the release of energy. Let us now consider a randomly formed nucleus with radius r2 located to the right of the maximum of the curve. This formation is also initially caused by thermal fluctuations in the melt, which lead to a corresponding increase in the Gibbs energy in the short term. In this case, a reduction of the nucleus radius is only possible by adding energy, which means by increasing the Gibbs energy, and will therefore not occur spontaneously. The nucleus does not disintegrate. Rather, the solidified nucleus will spontaneously increase its radius by decreasing the Gibbs energy. Of course, this can only happen if more molecules from the melt attach themselves to the nucleus. This is the beginning of nucleus growth and the solidification process begins. The critical nucleus radius, above which a nucleus can grow stably, is obtained by determining the radius at which the Gibbs curve shows a maximum. By calculating the first derivative of the Gibbs function and setting it to 0, the critical nucleus radius can be determined. This results in the formula shown for the critical nucleus radius. Let us consider a small example at this point. The supercooling of metals during homogeneous nucleation is of the order of about 25% of the solidification temperature. For iron with a solidification temperature of 1810 Kelvin, for example, this means that supercooling of about 450 Kelvin is required for homogeneous nucleation. If one assumes a surface tension of 2.5 joules per square meter, a specific heat of solidification of 268 kilojoules per kilogram and a density of 7.87 grams per cubic centimeter, the above-mentioned supercooling of 450 Kelvin results in a critical nucleus radius of about 9.5 nanometers. About 300,000 atoms are then required for the formation of such a nucleus. It should be noted at this point that the relatively high supercooling of 450 Kelvin applies only to homogeneous nucleation. Heterogeneous nucleation, on the other hand, requires only a fraction of this supercooling, so that homogeneous nucleation in molten metals is rather unlikely. In another video, heterogeneous nucleation is explained in more detail. As can be seen from the diagram for the change in Gibbs energy, energy must be supplied for nucleation in order to increase the Gibbs energy accordingly. This is done by thermal fluctuations in the melt, which can provide this amount of energy locally and for a short time. This amount of energy to be supplied is also referred to as activation energy for nucleation or free energy barrier. only under the assumption that a randomly formed nucleus is so large that the change of Gibbs energy is negative from the start, crystallization occurs directly with release of energy. However, the probability that such a large nucleus is formed is low due to the large number of atoms required for this. According to the formula derived, supercooling obviously has a decisive influence on the critical nucleation radius. The greater the supercooling, the smaller the critical nucleus radius. At the same time, as the critical nucleation radius decreases, the activation energy also decreases. Thus, with increasing supercooling, it becomes more and more likely that nuclei capable of growth will form. A large number of nuclei can then form, resulting in a fine-grained microstructure. However, this only applies as long as the supercooling is not too great. This will be discussed in more detail later. The activation energy for nucleation can be determined by using the critical nucleation radius in the formula for the change in Gibbs energy, showing the direct relationship with supercooling. For the example given earlier, this results in an activation energy in the order of about 9.5 times 10 to the power of minus 16 joules. It should be noted that both the activation energy and the critical nucleation radius increase with decreasing supercooling and become infinitely large when the solidification point is reached. Stable nucleation is therefore not possible at the solidification point. As already explained, the activation energy is provided by thermal fluctuations in the melt. Several small fluctuations are more likely than a single large fluctuation. This explains why the number of nuclei capable of growth increases as supercooling progresses. Strong supercooling is therefore usually desirable, as it leads to a fine-grained microstructure that is characterized by high toughness and strength. However, there are limits to the increasing nucleation rate with increasing supercooling. This is because diffusion processes in the melt and in the nucleus are necessary for nucleation or nucleus growth so that the atoms can attach to each other. With increasing supercooling, however, diffusion processes decrease due to the lower temperature. This applies to diffusion in the melt as well as to diffusion across the phase boundary and diffusion in the nucleus. There are no longer enough particles coming together to form and grow a nucleus. From a critical supercooling, therefore, fewer and fewer nuclei are formed. The diffusion-related accumulation of particles per time can be described by the so-called Arrhenius equation, which assumes an exponential dependence on temperature. In this equation, Qd is the temperature-independent activation energy for the diffusion process and Kb is the Boltzmann constant. At the same time, it must be taken into account that the nuclei capable of growth must also reach the critical nucleus radius. This can also be described with the Arrhenius equation. The number of growthable nuclei formed per unit time can thus be determined analogously to the previous formula. Delta Gc denotes the temperature-dependent activation energy for nucleation. Since the total nucleation rate ultimately depends on both of the previously described influences, the overall relationship results from the multiplication of both relationships. Note in this relationship that the activation energy for nucleation depends on supercooling. The diagram shows schematically the influence of supercooling on the nucleation rate according to the derived relationship. It can be seen from the diagram that at low supercooling, the activation energy for nucleation is much greater than the activation energy for diffusion. The formation of nuclei is therefore inhibited by the high energy required for nucleation. Thus, only a few nuclei are formed and consequently a coarse-grained microstructure is obtained. If the supercooling is too strong, the situation is similar. Due to the low temperature, the activation energy of diffusion is much greater and now inhibits nucleation, although the activation energy for nucleation would be very low. In turn, only a few grains are formed, which leads to a coarse-grained microstructure. So there is a maximum nucleation rate at a certain supercooling. Obviously, most nuclei can form at this supercooling, resulting in an extremely fine-grained microstructure. However, the diagram also shows that excessive supercooling can even completely suppress nucleation. Such a strongly supercooled melt then solidifies without crystallization. The particles are frozen, so to speak, before they could form a crystal structure. We then speak of amorphous metals or metallic glasses. Amorphous metals are characterized by extremely high hardness and strength and are limited to a few specialized applications due to the costly manufacturing process. High-end golf clubs, for example, are made of metallic glass. To conclude this video, a note on the individual terms in the formula for the change in Gibbs energy. In it, we have attributed the change in Gibbs energy to the change in volume energy and the change in surface energy. In fact, deformation energy can also play a role in phase changes. While these can be neglected during the transition from the liquid to the solid state, they must be taken into account for phase transformations in the solid state. In the given equation, there is then a third positive term which takes these effects into account. Furthermore, it should be noted that the derived formulas for the critical nucleation radius and the activation energy are based on the assumption of a spherical cluster. In isotropic metal melts, this assumption is quite justified. However, for liquids consisting of long molecular chains, such as alkanes, a cylindrical nucleus is more likely to be assumed. It should also be noted that a spherical shape has the smallest possible surface in relation to its volume. A spherical cluster therefore shows the smallest possible activation energy for nucleation. For other nucleus shapes, the activation energy is higher. I hope you enjoyed the video and found it helpful. Thanks for watching.